Good evening, and welcome to the Structural Engineers Foundation of Washington 10th Annual Fall Forum. It is hard to believe that we've been holding these forums annually since 2011. My name is Craig Roberts, and I am the chair of the SEFW, and will be introducing the forum and tell you a little bit about SEFW. SEFW is a nonprofit that is associated with the Structural Engineers Association of Washington, or SEAW. We have a charitable mission to advance the profession of structural engineering through scholarships, education, research, and outreach. Over the years, we have worked closely with SEAW and other organizations to fund activities that fulfill this mission, including scholarships, STEM events, research projects, and also this Fall Forum lecture series. SEFW is a 501(c)(3) nonprofit, and funds donated go to support activities that fulfill this mission. We welcome donations from individuals and corporations at any time. An easy way to donate is through text. So if you feel inclined this evening while you're watching this, you're welcome to text in a donation by following the instructions here, or you can visit our website. Many corporations donated to SEFW at this time for our Fall Forum, and we're pleased to recognize them tonight. Firms were invited to donate at one of several levels, and we are especially grateful for PCS Structural Solutions, who donated at the Platinum level. As a Platinum partner, PCS was invited to submit a short video of support to be shown during this virtual event. Thank you, PCS, and here is the video. Again, thank you, PCS, for your Platinum donation and continued support of SEFW. Our other sponsors are listed here, and I'd like to recognize some of our gold sponsors, specifically CKC Structural Engineers, DCI Engineers, and Seattle Structure. Thanks to these firms and other firms and individuals for contributing to SEFW. Again, their donations will go directly to fulfilling the SEFW mission this next year. The last group of people I'd like to recognize is our dedicated board of directors. These individuals are focused on the mission of SEFW, for forging partnerships and distributing funds to best fulfill the mission and benefit the structural engineering profession. We are fortunate to have a representative from SEAW on the board and a great administration team. I'd like to recognize Kale Ash and Margaret Rose Hancock, who helped recruit our speakers, and also to Angela Gutola, our minister, who was key in organizing this event tonight. Lastly, a couple things about the event tonight. First, we have provided a downloadable event program, which can be accessed via our website. If you visit www.sefw.org and go to the forum page button in the upper right-hand corner, you can select the event program and then view a very nice PDF that gives you more information on SEFW and tonight's events and our speakers. After the presentation tonight, we will have an opportunity for a question and answer with our speakers. For this virtual event, our Q&A format is interactive, and we'll be monitoring it during the live presentation. If you are on Crowdcast, you should use the Ask a Question box in the lower right-hand corner of your screen. You can input your questions there and vote up questions that are already written that we'd like to see answered. We're also broadcasting this on YouTube, and we'll be monitoring the chat window there for questions as well. We'll present as many questions as we can to our speakers at the end of their remarks. I now have the honor to briefly introduce our two speakers tonight. Maureen Elanga is an architectural historian and author who published works including Seattle Architecture, A Walking Guide to Downtown, and Bridges of Seattle, which was just published this year. She has written extensively about the history of Seattle's development and about the people and events that have shaped the Emerald City. She is an outstanding researcher and, from what I understand, put in an extra effort to learn about bridges from all corners of Washington for tonight's presentation. She holds a master's degree in architectural history from the University of Washington and an undergraduate degree in art history and communications from the University of Oregon. Maureen has worked as a business manager for the Arcade Journal here in the Northwest and is manager of the Cities and Buildings database at the University of Washington Library. Maureen was born and raised in Portland, where she developed an early interest in the built environment from her father, who was an architect. She now lives in Seattle with her husband and 2 children. Speaking with Maureen will be John F. Stanton, the Thomas and Marilyn Nielsen Professor of Engineering in the Department of Civil Engineering and Civil and Environmental Engineering at the University of Washington. John has a bachelor's and master's degree in mechanical sciences from Cambridge University, a master's in civil engineering from Cornell University, and a PhD in civil engineering from the University of California, Berkeley. He worked in design practice for 6 years in Britain, France, and Canada before joining the UW in the late 1970s. He became a full tenured professor in 1992, primarily teaching structural engineering. Since that time, he has taught thousands of engineering students and participated in research on seismic design, precast concrete, framing systems, and a host of other design issues. John was born in the UK and now lives in Seattle with his wife. With that, I'd like to offer a warm welcome to Maureen and John and thank them for teaming up to present the forum for us tonight. On a note, we have more than 400 people registered for this event from 9 U.S. states and 5 countries. So to everyone viewing from home in all corners of the world, I'm pleased to turn the time over to Maureen and John, who will be presenting Bridging Washington, the history, structure, and engineering of Washington bridges. Maureen.
Hi, thank you. I'm very excited to be here, and I thank the forum for inviting me to participate tonight. We're going to be looking at several different types of bridges, as you can see on the list there, and I will just jump right in. Early Washington bridges, not surprisingly probably, were all timber trestle bridges. In territorial days, property owners could build their own bridges, and they were permitted to charge tolls. Communities coalesced around water, which was great for transportation links, but caused problems with getting around on land. So in Washington, however, the first permanent steel bridges were built by railroads for the railroads. But our early road bridges, really our bridge heritage in Washington, is really tied to the growth of automobile use. So for the years from 1910 to 1920, a dramatic increase in automobile use. There were 9,000 registered automobiles in 1910. By 1920, there was over 180,000 automobiles in the state. So the Jose Rizal Bridge was the first permanent bridge in Seattle, and like many of the first permanent bridges in the state, it was built of steel. This bridge carries 12th Avenue South over Dearborn Street. This bridge, though, is not crossing water. It is over a regrade, bridging the gap where they dug in for Dearborn Street. And for the first several decades of Seattle, all the bridges were temporary because they were going to be doing these major regrades and cuts. But steel was the earliest, but concrete although widely used later after World War I, we do have an early example concrete road bridge in Monroe Street Bridge in Spokane. This was actually the third bridge in this spot. There was a timber trestle bridge that stood for a year before burning down, and then a steel bridge stood for about a decade, but it was deemed unsafe. It vibrated and it was sagging in the center. So a representative from the Good Roads movement, and they were very active in getting highways and roads and bridges built, said it would have to go. So they built it with this concrete arch bridge, which was the longest concrete arch bridge in the country when it was completed by a foot. And it's probably the reason that we had earlier concrete bridges here is that Washington doesn't have a big steel tradition, but we did have a thriving Portland cement industry. So we did have an early bridge, and that bridge is a historic bridge. It has been completely rebuilt in 2005, but retains the original arch span. Now, another type of bridge, those two were both high fixed bridges, but we of course have movable bridges, drawbridges, and bascule bridges are the most common type. They are named bascule for the French word for teeter-totter, and that refers to the way that the movable spans are raised and lowered on counterweights. And they, if you've ever driven in a city over a river, you've probably driven over a bascule bridge. Now, Seattle had a lot of desirable qualities as a place to build a city, but as I mentioned with the regrades, they had a lot of ambitious major engineering projects to do. And this South Lake Union area, that's where Amazon and tech companies are today. At this time, that was David Denny's lumber mill. And back as early as the 1850s, one of the major engineering projects that they wanted to do was to cut a canal that would link Lake Washington at the east to Puget Sound to the west, and connect them by way of Lake Union in the middle. And that is why actually it is called Lake Union, because it was going to be what united these two waterways. So it got going in fits and starts by private investors, David Denny being one of them. But eventually, the federal government took over the project, and this is how far the creek had been dug between Lake Union and Salmon Bay at the time that the government got involved. Now that canal, of course, is 250 feet wide and 100 feet deep down the center. So there is the Army Corps of Engineers. They undertook the project, which was include 2 waterway cuts, one at Mott Lake between Lake Washington and Lake Union, and another one at Fremont. And then the city was responsible for 4 bridges. The Corps of Engineers were also building the locks and spillway, but the 4 bridges were up to the city to finance and build. The first, Fremont, there had been a bridge at this site since the 1890s that spanned the natural creek that we just saw a photo of, which was the natural outlet of Lake Union. So this bridge was built, this is the second bridge actually, this is not the 1890 bridge. This was built longer to accommodate the canal being dug. In 1911, there was a temporary bridge built at Stoneway that you could see in the distance beyond the bridge under construction here. And it was temporary, but people got so used to using it, they wanted to keep it. They asked the federal government to permit another crossing there, but they said nope, so it had to go. So unfortunately, no crossing there. So 9 months after the completion of the locks, the first bridge was finished, the Fremont Bridge. And then the Ballard Bridge is the next one. And this is the Salmon Bay Bridge. There had been a crossing at this same spot at 14th Avenue West since 1890s. This one was built in 1910, temporary with a swing span to allow for the construction of the locks. And there is still evidence of this bridge. If you're familiar with Seattle, if you drive around Ballard, you'll see on 14th Avenue West where it's wider and there's a gravel parking strip down the center. That's where this bridge came out and that carried the train tracks. So that's why it's like that. So the Ballard Bridge was completed 6 months to the day after the Fremont Bridge was completed. This photo was taken in the 1930s. You can see that there's a timber trestle approach. Those were replaced by the end of the 1930s, but the first 3 bascule bridges had timber approaches until that time. So they were moving along pretty well. They'd opened 2 bridges in 6 months, so progress. However, for the bridge, the University Bridge, was a 2-year delay before it would be done. And part of that was controversy over the location. This was originally, it replaced the Latona Bridge, which was at 6th Avenue Northeast, and that served an area called Brooklyn, which we now just call the University District, and the University of Washington to the east. And people wanted a bridge that would get them closer to the university. So funding was rejected until they decided on a site at 10th Avenue Northeast, which is where the University Bridge opened in 1919, but that was a costly delay. They had to renegotiate contracts at wartime prices during World War I. So this bridge at $825,000 came, that was more than what the first 2 bridges cost combined. So it was a costly delay. This photo obviously is later. This is from the 30s. And I'm showing it because you'll notice the steel mesh grating on the road deck. That was installed in 1932, and that was the first use of that technology in the country. And all of the bridges had creosote timber on the decking, which became rather slippery when wet, which is quite often in Seattle. And this bridge was particularly dangerous. It averaged 6 deaths a year because of the slippery conditions. And this grating completely eliminated any deaths due to those conditions. And it was put on all the rest of the bascules by the end of the 1930s. Now, it would be another 6 years before the 4th and final bascule bridge was built. But ironically, its foundation piers had been in place since 1914. And that is because the Montlake Cut between Lake Washington and Lake Union cut Montlake Avenue, and they built the piers at the time. So people who wanted to go cross at Montlake would have to take a detour of 5 miles, take one of the bridges to come back up. It was very inconvenient. And the area, though, that it served east of the university was growing rapidly. This photo is clearing of Fremont Lake. The university had been there since 1895, and you would think that people would pass funding for this bridge, but it was rejected over and over and over for a decade. There's that area just 9 years later. So why, in 1919 and 1920, did the citizens deny funding? Well, class resentment is probably the biggest reason, and that may sound cliche or intellectually lazy, but in 1919, the first citywide general strike in the nation was held in Seattle. So the tension between the working class and the moneyed class and people who lived in these fine homes was very real. And so they had to get creative. So the University Stadium had just been built in 1920. So bridge boosters teamed up with influential Husky fans and promoted it as the Montlake Stadium Bridge. And it didn't pass, a couple more times didn't work, but finally on the 8th try with momentum building for this stadium bridge, it passed in 1924. So the Montlake Bridge opened in June 1925, proving that you can find common ground to get anything done if you try hard enough. The bridge was stylistically different. The first three were done in a more utilitarian style. This was done in a collegiate Gothic style to match the university buildings, and it was designed by Carl Gould, who also designed the campus buildings. And with the completion of that, it was the completion of a long dream to build the Lake Washington Ship Canal. And John now will talk about bascules.
Oh, thank you, Maureen. That's a fascinating and very interesting description of how we tried to cross that waterway from Lake Washington down to the lock, to Lake Ocean, because clearly that's a big impediment and you need bridges to get over it. I'd like now to turn the page a little bit and look inside some of these bascule bridges and just see how they're built and how they work and what's important to them. There's a few things which are relevant. One is that they've got lots of moving parts, and therefore in some sense they're like a machine rather than just a fixed bridge. The spans which you can use are also fairly limited by the machinery that you put inside in order to lift them and lower them. As Maureen pointed out, you do need to balance the weight on them in order to accommodate that, with a counterweight at the back and the span in the front. And of course, the lighter you can make the whole thing, the better off you are, because then the less energy you need to use in all the machinery. So this is a picture of the original Fremont Bridge proposal, and you can see it in the kind of up position and the down position now. And a couple of things that we could point out. One is where the red circle is there. That's where the pivot point is. It's essentially the kind of balance point of the teeter-totter as it goes up and down. And another one you can see is the counterweight. There's the green circle on the left there. And you can see that the backspan, i.e. the distance from the counterweight to the pivot point, is really quite short. And you don't have much choice in that, because that point has to go down underground. And if you made it really long, you'd have to dig an enormous hole underground to accommodate it. So if you've got a short backspan, then you need a heavy weight on the back, and those weights are actually pretty big. If we go to the Fremont Bridge and take a look and just see as built, we can see some of those same features. There's a little line there saying axis of rotation, and that indicates where the pivot point is, that it swings up and down. You can't really see it from here because it's kind of hidden behind the concrete sidewall, but that's where it is. And on the front, we've got these two steel supports, and that's where the bridge comes down and sits on the concrete on the front, so that when it's in the down position, then the weight is supported on the front, and it stops the whole thing from tipping over forwards actually into the water. We can take a look at inside and see what the gears look like to lift this thing up. And they're pretty monstrous. You can see they've got an arrow there pointing to the rotation pin, and this is the pivot point. This is just a giant pin that the whole thing swings around on. What actually drives it is what I've called the circular drive track at the back. And this is a big circular track, and it's driven by those gears that you can see down in the bottom right-hand corner. And again, they're pretty big. How do they make them? Well, there was a fairly thriving shipbuilding industry in Seattle at the time, and to build ships you need big machinery, and that, I suspect, is part of the reason why we are able to produce these very large machine parts. You can't readily see inside, but if you drive over the bridge, you can still see the drive track. If you walk across on the pedestrian side, on the west side, you can see these big greasy drive tracks there, and they are indeed the working guts of the bridge. I think we should take a look at the steel bridge construction in the Bascule era and just see how they made these things. And some of the important technology is, when you make a bridge, is that you have to make it in pieces. You cannot just make a whole bridge and drop it in place suddenly. If you make it in pieces, you have to connect them together. And the way you connected them together at the time was using things called gusset plates and rivets, and we'll see those here. So here we see, this is again the Fremont Bridge, and we can see a lot of the pieces of the big pieces of steel, the columns and beams and things, all coming into this one point. And at that point they're connected together by the gusset plates, which are giant plates which are riveted to everything else around them, so that everything is therefore connected together. And you might think, well, there's only just one, but no, that's not true. There's another little one up here, there's another one down there, and I suspect if we looked hard enough, there'd be a few more in the picture. And really what this goes to show is that the gusset plate business was pretty complicated when you were trying to connect everything together, and all these plates were kind of laid on top of each other in a really fairly artistic, craftsman-like way. So there's really a lot of craft went into building these things. So the little round things that you see there are not bolts, they're rivets. And we should do a little take riveting 101 here, I think, just see how this is all done. If you've got two plates, maybe two gusset plates, that are sitting next to each other and you want to connect them, the first thing you do is drill a hole. Then you heat up a rivet to red heat, cherry heat, and then you put it in the hole. Then you bring up a riveting tool, which is a thing like a big heavy hammer which sits behind it on the head side. You bring up another riveting tool on the opposite side, and then you whack it so that you form a second head on the rivet when it's still hot. At that point, you're sort of done. You can take away the riveting tools, and if you watch it, the rivet will shrink as it cools. And as it shrinks, then it clamps the two plates together, and eventually it goes cold, and it's finished doing all its shrinking. At that point, the two plates are clamped together pretty tightly, and as they're clamped together, if you tried to pull them vertically, in this case, the direction of the yellow arrows, you couldn't do it, because there'd be a lot of friction holding them together. And that is basically the way that all of these riveted joints worked. I think it would be useful to look and see how it's done in practice. So there's a couple of pictures here I took from Peter Stackpole's wonderful book about building the San Francisco Bay Bridge, and these images are from him. This is the kind of cook of the business. He is the one who's heating up the rivets, and he's sitting there smoking a cigarette, minding his own business. And you can see there's kind of a gas burner next to him, and it's got a lot of things that look like mushrooms growing in it. They're not. Those are rivets, and they're heating up. When they're hot, somebody picks them up with a set of tongs and takes them to the place where they have to be put into the holes. And there's a riveting gang up there. And this is one side of it with the people with a riveting tool on the head of the rivet. I think these guys are forming the second head. On the other side of that piece of plate, out of the left of the picture, would be somebody with a tool to stop the rivet just popping out the other side of the hole. This is another picture just to give you an idea of how dangerous this work was. In the previous picture, you could see they didn't wear any form of ear protection, and riveting was a very, very noisy business. Up here, you can also see they are riveting on the very top of one of the towers of that San Francisco Bay Bridge, because the big piece of metal on the left is a cable saddle where the big suspension cables are going to go over. You can see there's another gas burner up there smoking away. You don't see a single safety line anywhere. And these guys are something like 300 feet above the water. So tragically, it's not surprising that several people died on most of these big bridges. Well, if we come home to Seattle and see what the riveting looks like there, this is something you can get very close up to. And this is the Ravenna Arch Bridge. And I think what it points out is a couple of things. One is there's a pin at the bottom. And you might ask, well, why do you have a pin at the bottom of an arch? And the answer is, if you don't have a pin, if the soil were to move, then you'd induce some stresses in the steel that you probably don't want. If you put the pin in there, then it allows the steel to move and you don't get any stresses in it. So it's a great way of dealing with either temperature effects or potential soil movement. What that means, though, is you've got to bring all the forces from the arch down to this one very small point. And what you see is some really quite clever, I would say almost artistic, arrangement of the plates and the careful riveting of them all together to bring the forces down to this one point at the bottom. So how have things changed today? Well, back then we did riveting. Riveting took something like a 4 or a 5-man team to do it, to put in each individual rivet. And that in today's terms is incredibly expensive in terms of labor. So since then, what we've done is switched over to very high strength bolts, which do the same kind of job as the rivets. They clamp the plates together in a very similar way, but in today's world, there are now bolting systems that you can put the bolt in and tighten it up just from one side. You may wonder if you've got a nut and a bolt head, how do you do that? But that's another story that we won't go into today. Well, if we think about the kind of overall steel bridge design and not just the connections, then there's a few things that stand out. If you're making steel bridges, steel is pretty strong stuff. Therefore, you don't really need very much of it. If you don't need much of it, then the members get to be quite small and skinny. And if you make them quite small and skinny, then immediately you bump into the problem of buckling. So what we find in steel structures is that two of the big problems are, number one, buckling, and number two, the connections. How do you connect the pieces together? Second thing is, because it's so strong, you really need to put the material only where you need it. And that's why we wind up with configurations like trusses, which seem to have an awful lot of air in them, which is quite true. But you put the steel just exactly where you need it and nowhere else, and that's how you get that configuration. And the last thing is, how do you put these things together? Well, back then, they put them together in what we would call a stick-built fashion. You bring each individual piece and you rivet it together. Today, it's a more common practice to weld together bigger pieces, to take those bigger pieces out to the site and then to bolt them together. Because welding is well suited to work in a well-controlled shop where you've got good weather. Bolting is better in the outside world where welding is pretty expensive, and particularly crane time is expensive. You don't want to have a crane holding onto a piece for a whole day while you weld it together. So let's move away then from the bascule bridge weld to some fixed steel bridges and just see how they work. And a fixed steel bridge, of course, is a bridge which doesn't go up and down like a bascule bridge does. And a couple of the examples of these are typically slightly later than the bascule bridges were built. They were kind of in the 1930s. Here's the Aurora Bridge being built. And the first thing you should note in this picture is that the ship, I think, is just getting out in time because it's leaving Lake Union and the masts are higher than the bridge. And if they left it a few more days or possibly weeks, it would never ever have got out. So clearly someone got it out in time. The second thing is that the bridge is built using what they call the cantilever construction method. And what you do here is you build each side, and you see the main supports, and then they built it back to the concrete structure behind that, and that stabilizes it. So now you can build these cantilevers out until they meet in the middle, and that means that you don't need to put any false work, any scaffolding out there in the water, which would clearly be a major mess if you did. So this cantilever construction method becomes pretty important for many, many different types of bridge, and we'll see it again a couple more times. Here's the Aurora Bridge today, and really the thing I'd like to point out here, which may be a little hard to see, is that many of the secondary bracing members here, which don't carry super big forces, they're made up of a really delicate lattice work of small pieces all riveted together. And that indicates what was true at the time, which was that basically labor was cheap and material was expensive. And so what that meant was that you bust yourself to try to use as little material as possible, even if it meant making a lot of connections. And that's why you come up with this kind of filigree of fine pieces. Other bits, you can't really do that because here we are down at the basic support of the bridge. And I think the thing I'd like to point out here is that there are an awful lot of pieces coming in at strange angles, and yet they all have to be connected together with these gusset plates and rivets. And in a geometric sense, this is a complete nightmare of how you manage that. There's one more thing here. I'm sure some of you have seen down the bottom, there's some more modern-looking green plates down there. These are isolation bearings, seismic isolation bearings, which were put in 2011. And what they do is that they allow the bridge to move around a little bit on the support. The bearing is like it's kind of a saucer-shaped cooking pot with Teflon on the inside. And it allows the foot of the bridge to slide around inside that giant saucer-shaped cooking pot so that it can displace a bit, and that massively reduces the forces on the bridge due to earthquakes. I think you can imagine that putting that thing in retroactively meant that somehow you had to pick up the bridge with one hand and then put the bearing under with the other hand and then quietly let the bridge down on it when you were all finished. So just from a construction point of view, that was a remarkable operation. A couple of other bridges here. Deception Pass, the same kind of era in the 1930s, again built by the cantilever method. And this is a particularly difficult one because the currents under that bridge are wicked as the water flows in and out due to the tides. So if you fell off that bridge, then it was probably a bad outcome. Here we go to the last of these ones, which is a later bridge built in 1966. And this is the Astoria Bridge joining over the Columbia, or the mouth of the Columbia. And it's rather different in a couple of ways. One is that they were no longer using riveting technology. That went out in roughly the 1950s. That was kind of the changeover. So here it's all using bolted technology. It also was built using cantilever construction. And a slightly different thing you see at the top of the columns. The columns are very narrow, and therefore they could not carry any bending, and so they really had to anchor this thing back to the shore and then build it out to the column and then cantilever it out from there until they finally met in the middle, which is a huge span. So this is, in fact, the longest cantilever truss bridge, continuous cantilever steel bridge in the US, and that is still true today. 1,233 feet on the main span. So that's getting about as long as you can with these things. And we do get another view from what the maintenance crews see when they go up there, and the mist is flowing through on the Columbia underneath. What a fabulous view. You can notice here also that these secondary cross pieces are not made up of those little spindly filigree pieces. They're made out of solid beams with holes cut in them. And here what we're seeing is that the cost of labor and material have started to switch over, and so it becomes more economical to just take a rolled steel beam, chop a hole in it to keep the weight down, and then put it in place. So what do you do if you want to make an even longer bridge over water? Well, I think we'll hand over to Maureen to answer that question.
This is the Medina Ferry landing, as you can see, 1915. Prior to 1940, from 1890 to 1940, the only way to cross between Seattle and the east side of Lake Washington was by ferry. There was also passenger steamers. There were about 30 steamer and ferry landings that lined the east side of the lake, yet only 3 of them accommodated vehicles. And that was stops at Kirkland, Bellevue, and here at Medina. And here is a horseless carriage followed by a horse and carriage waiting to get on the Bellevue ferry. If you did have a car, you could drive to Seattle, but you had to take a 26-mile, 1-hour trip around the south end of the lake and back up north to the city. There was no vehicle access to Mercer Island. And the area of Bellevue and Mercer Island were very, very rural. This is right what was up behind that ferry landing. Farms, the economic center of the east side was Kirkland. They had woolen mills and shipbuilding in Kirkland, but Bellevue was strawberry farms and agriculture, very sparsely populated. After World War I, Mercer Island was considered a prospect for residential developments if only you could get a car there. So they built the East Channel Bridge connecting the northeast side of the island to Bellevue. And this is the same area where the I-90 connects today. And this did increase the residential population a bit in the 1920s, and there was some interest among islanders for a bridge across the lake to Seattle. But it was problematic. The lake's very deep, muddy bottom, so traditional bridge on piers is problematic, and there just wasn't enough interest. This gentleman, Homer Hadley, though, he was way ahead of them. He first proposed the idea in 1920s. He was a engineer who had experience building concrete ships and barges in Philadelphia during World War I. So he was very keenly aware and interested in the floating possibilities of concrete. And when he was working as an engineer in the architecture department of Seattle schools in 1920, he proposed this idea of a bridge on concrete pontoons. And it didn't go anywhere. A year later, he left to take a job with Portland Cement to promote its use for large-scale projects. And that same year, he proposed the idea to the American Society of Civil Engineers, and that got people in the city talking about maybe this is something we could consider doing. And he was a conservative politically. He did not want this to be built by the government. He wanted it to be funded privately, but no bankers or private investors were interested. They thought the people over there are too poor and it's too sparsely populated. It would never pan out, and they started calling it Hadley's Folly. But then, 17 years later, in 1938, war was happening in Europe, and the United States was dealing with the Depression, and Franklin Roosevelt's administration started the Works Progress Administration, and they made an offer to pay for 40% of the cost of the bridge to connect the highway bridge, and the rest could be paid off by the state tolling authority. And despite his opposition to FDR and the spending, Hadley saw this as an opportunity to realize his dream. So he proposed the idea to Lacey Murrow, and that's that gentleman there. He was the director, state highway director, and he convinced him that it would work, and he assembled a team of the best engineers in the state, and this is them posing as the shovel crew. Now, the WPA offer was set to expire by the end of 1938, and they proposed a tunnel through Mount Baker, which of course is where it is, but people didn't want it. People didn't like it. They had the NIMBY problem, and so there was debate over the location, and the federal government said, enough already, build it, or else we're going to revoke funding. So they broke ground on it 2 days before the end of 1938, just in time. But Murrow asked Hadley to stay out of the public limelight of the bridge because of the Portland Cement Association. He would see it as conflict of interest. He said, you'll get credit later after it's built, just keep quiet for now. And it opened in July 1940. Its floating span, 6,620 feet. It was the longest floating structure in the world when it was built, and the first floating bridge made of reinforced concrete. And it cut travel time from 1 hour to 7 minutes from east side to Seattle. And it was a resounding success. The bridge became an attraction in itself. People would come just to drive over the bridge, but it also sparked a massive amount of growth on the east side, particularly after the war. Between 1940 and 1950, the population and property value at Mercer Island increased 300%. It was so popular that the toll was paid off 19 years early. And this photo, Governor Langley is taking a ceremonial last toll from a Como News reporter there. But the growth was really concentrated in Bellevue and Mercer Island. And by 1948, Kirkland, who were further north, they wanted another floating bridge to serve their community. But it would be another 15 years before it was built. The funding for the Evergreen Point floating bridge, was approved in 1953, but debate over location once again went on and on. It finally got whittled down to two possible locations, one being at the Navy Standpoint and the other at Montlake to Evergreen Point. And this route was preferred by the Navy. They didn't want the bridge so close to Sandpoint. And it was preferred by Governor Rossellini, so that's the one they went with. And there's Governor Rossellini with the giant novelty scissors, cutting a standard 1-inch ribbon. And it did deliver the growth that they had hoped. It paid its toll off even sooner than expected, 21 years early. It was supposed to be paid off by 2000, and it was paid off by 1979. But the traffic relief that it was supposed to have created was totally erased by the population growth. So in 1989, a third floating bridge was constructed directly, like, adjacent to the first one. After that third bridge was in place, they went about refurbishing the original bridge at 50 years old. They were refurbishing the pontoons, and they left these pontoon hatches, you can see there, they left those open over a Thanksgiving weekend in 1990, and it happened to be a very blustery one. A storm came in, and those open hatches got filled with water. Workers attempted to pump the water out, but it was too late. One pontoon sunk, and then they all went down like dominoes. So that the Lacey V. Murrow Bridge floating section had to be completely rebuilt. So here it is as it is today. You can see on the right the Lacey V. Murrow Bridge, the only original feature being the approach, steel arch, through arch approach, and the Homer Hadley Bridge, the 1989 bridge, named for Homer Hadley, who finally, 22 years after his death and 49 years after his bridge was built, he finally got his due credit. So now pass it over to John.
Thank you, Maureen. Say on a historical note, it was shortly after I first came to Seattle that I remember crossing the Evergreen Point Bridge and having to pay the toll. And at that time, there was nothing electronic at all. As you went over the bridge, there was a basket, and you tossed your dime into the basket as you went. And the trick among the slick people was how fast could you go while you tossed your dime in there and still get it in the basket. But that didn't last long. Okay, well, back to the techniques of floating bridges. There's a nice picture of an early floating bridge, which was given to me by Patrick Clark from the DOT. And he didn't record exactly where it is, but he did say this was not a washdot bridge, and you can tell that because there are elephants crossing the floating bridge, and WashDOT does not have provision for elephant loading in its specifications. So quite clearly, this is not a WashDOT bridge. It also appears to be in some trouble because there's people jumping off and it's sinking everywhere. And we hope we can do a little better than that now. So if we go back to the question that Maureen originally asked, which is, what are the conditions which would persuade you to build a floating bridge? And I think the answer is pretty much this. If you have a long bridge that you've got a wide body of water you've got to get across, it's deep and it's got a very muddy bottom on it. What that would mean is that the columns that you'd have to put in for a conventional bridge would be enormously tall and they would be enormously expensive. And so this is really where the floating bridge comes in. You simply put the bridge deck down on the water, you make it a hollow box so it floats, and then you're off and running, and you can do it a lot more cheaply. Well, you might be suspicious and say, I don't think concrete floats. Do these things really float properly? Well, the answer is if you put enough air inside it, you can make anything float. And that's exactly the principle that we use with the concrete pontoons. And of course, we use it for ships. Steel ships have been around since the middle of the 19th century, and they float, and steel's heavier than concrete. Why do we make it out of concrete rather than steel like a ship? Basically because the concrete solution is cheaper. We've also had significant experience with these things. Homer Hadley himself was doing it during the World War I era. And a good reason for making ships then out of concrete was that they were non-magnetic. And people were running around with magnetic mines, clamping them onto steel ships and blowing the ship up. And of course, you can't do that with a concrete one. We make things like LNG, liquefied natural gas barges. They are giant floating platforms. Docks the same. And even the UW-ASCE has a concrete canoe team. And they make concrete canoes which they paddle and race in. And those things are incredibly light and thin. So if we look at the Lacey v. Morrow Bridge, which is known in the trade as the LVM, to the cognoscenti, it basically looks like a giant box with some internal dividers. It's kind of an 3D egg crate, if you like. This is what it looks like inside. There's a few things you have to worry about, like movement of these bridges. And the first one is, what about longitudinal movement? The bridge is roughly a mile long, and from summer to winter, this is what it does. It gets longer. And it gets longer by something like 3 feet. And therefore, you have to make allowance for that elongation at the ends by having joints which will accommodate this kind of elongation and obviously the contraction in the winter when it cools down again. So you need a big expansion joint, and those alone cause their own share of problems. Transversely, i.e. across it, what do we do there? Well, the problem is that if you don't anchor it down properly, the bridge might blow away, or it might be carried away by the tide or the current. And certainly in Hood Canal, it's tides, and in Lake Washington, it's mostly winds. And there are a couple of floating bridges in Norway, and they are usually at the mouth of a fjord, and of course there's a river coming down there, and in that case it would be the river current that you have to anchor them against. So we put in anchor cables, and these are fairly flat, nearly horizontal. And at the far end, there's a couple of different types of anchor that you can use. And one is what we call a gravity anchor. And crudely, that's just a big bucket full of rocks. It's very big and there's a lot of rocks in it. And that works very nicely if it's sitting on competent soil. If the soil is very soft, then the bucket of rocks would sink into the soil and move around. And so there, typically, what you would do is use a blade anchor, which is more like the anchor of a ship. And it cuts into the soil, and then it picks up a lot of weight of soil. So this is a gravity anchor. This one's actually out at the Hood Canal, and you can see this is the bucket, and they're just dropping it between two giant barges and a big gantry crane, just dropping it into the water where they want to, and then they drop the rocks in later. This is a blade anchor being constructed, and you can see there's a kind of steel triangular shaped thing which is a clevis with a little hole at the front end, which will be the cable will be attached to using a shackle. And at the back end, it looks like there's a wall going to be constructed of reinforced concrete because you can see the rebars there. And that is the flat part of the blade, which will engage a lot of soil, so when you pull on the anchor, it won't go anywhere. At the other end of the anchor, inside the pontoon, you need to fix it there. But you also need to make some space for adjustment. And so what you have here is a long red track, and there's kind of a movable dolly essentially in the middle of it, with the end of the cable attached to that dolly by a clevis. And if you want to move it, you undo the bolts which are holding the dolly to the track. You put a big jack in behind it, you pump up the jack and you move it to where you want it to, and put bolts in the new place. And in that way, you can adjust the length of the cable and the tightness of the cable. And the last movement you might be worried about is vertical. And how do we deal with that if you've got these anchor cables there? Surely they would hold the bridge down and sink it if the tide moved up too far. If we look at the vertical change in water level, in the lake it's not too bad. It's around about 2 feet. And this is adjusted by the Corps of Engineers by messing with the lock height. In Hood Canal, the tide is something like 12 feet from top to bottom. So that's a much more serious problem. But in both cases, what you can do is if the tide goes up, if you make the anchor cables flat enough, then the change in length of the anchor cable is actually very small as the tide goes up or the current goes up. So what happens to these bridges? Well, unfortunately, we've lost 2. When I came to the state of Washington, there were 3 floating bridges here. And since I've been here, 2 of them have sunk. And I assure you those 2 events are not related. I had nothing to do with their sinking. The Lacey v. Murrow Bridge went down, as Angela pointed out, as Maureen pointed out, in a big storm on Thanksgiving Day. And there was actually a perfect storm of events happened then. As they were trying to retrofit the bridge, they were cutting some of the deck off by using hydrodemolition, where you use very high pressure water jets to cut the concrete. That meant that the water was contaminated, so they were forced to store it somewhere and then pump it away later. So they were storing it actually in the bridge, because where better? This is a giant box which you can put stuff into. So they were putting it in the bridge and then pumping it out every 3 days or whatever. And it happened to be fairly full at the time that the Thanksgiving weekend came up. In addition to that, the cable hatches were open on the side. And in addition to that, a giant storm came up over the Thanksgiving weekend when there were very few workers around to do anything about it. And so the rest is history. The second bridge that went down was the Hood Canal. And this went down in February 1979 in a particularly heavy storm. And what happened there was that there were hatches on top of the pontoons for access so you could get inside to inspect them. Those hatch covers blew open as the water was washing over the pontoons. And as they blew open, of course, the water got into the pontoons. And you know what happens if you fill a concrete box with water when it's meant to be floating. So this bridge, also, we lost half of that bridge. So those are the kind of ordinary problems that you have to deal with if you own a floating bridge. There are some special problems which come up, which we can look at, just a couple of them now. And one of them is that in a floating bridge, it will move up and down with the water level. That means that you've got to get from the fixed part of the bridge, which is on the land, to the floating part, which is going up and down. And this is exactly the same problem that you have in a harbor when you have to get from ship to shore. You need a gangplank. And you'll get rotations at each end of the gangplank as the water level goes up and down. And we can see that here as the water goes down, the gangplank has to rotate. This is fine if you've got rubber-tired vehicles. They can deal with that little sharp kink at the end because it really is not that sharp. You don't even notice it as you drive across. However, if you have aspirations to put light rail over the floating bridge, then the picture changes because you have fixed rails, and rails do not like to go through these sharp angle changes. So you need some device in order to smooth out this sharp angle change into a gentle curve. And this is where we come across someone called Andy Phone, who is one of these people who is extremely and unbelievably smart, but completely unintelligible. And I think they probably happen quite often. Andy was sitting one day in a Starbucks playing with he's actually a rail track consultant designer from Britain. And he was sitting in Starbucks one day, this is the story he likes to tell. And in Starbucks, he was playing with some coffee stirrers and wondering about this and that. And apparently at this moment, he dreamed up the idea of making what he called a caesura track bridge. Well, caesura is an acronym, and I can't even remember what it stands for now. But what it does is that this track bridge is something like 150 feet long. And there is one at every end of a gangplank, if you like, or a transition span on the floating bridge. And it kind of bridges over that sharp rotation point. And what you can see is that the things that look like railroad ties, which are actually called bearer bars here, they are sitting on a little bearing underneath them, and they're different lengths. The ones at the end are longer than the ones in the middle. So that means the support bearings, which are holding up these railroad ties, are placed on a curve, and the whole system is arranged so that when the transition span rotates up or down, the two wing pieces, which are the gray things you can see at the side, they twist in or out just a little bit. And as they twist in or out a little bit, that horizontal curve that you see, which is where the support bearings are, that gives you a little bit of vertical curve. And the geometry is worked out in such a way that that vertical curve is exactly right, that the rails will be a tangent to the slope of the rails on the other part at the end, and you get a smooth curve instead of a sharp rotation point. And when you first look at it, it's mind-bogglingly complicated, and when you've seen it a few times, you think, my gosh, that's clever, because it's simple, and it really is. This is the one they're installing right now on the I-90 floating bridge, and it's not a super good photograph, but you can see the cross pieces are the railroad ties or the bearer bars. You can see that they are slightly different lengths, and you can see that they're built on a curve, and the support bearings underneath them, and you see the rails on top of them. As far as I know, this is the only place that has ever been built in the world, and so by definition, it's the first time this system has been used anywhere. Another problem you have when you own a floating bridge is that you probably need to let ships through, and this involves a draw span. And all of the early floating bridges had a draw span in them to let ships through. This is no longer true in Lake Washington, but the Hood Canal still maintains one, and we can take a look at a couple of them here. This is the original Lacey V. Morrow Bridge, and what you see is a section, one of the pontoons in the middle, was able to slide back between two neighboring pontoons on the side and therefore open to let ships through. Now this involved a somewhat awkward driveway, especially if you were drunk, because you'd be coming along going straight on the floating bridge, and suddenly you'd have to go through this rather sharp bend as you move from the original straight line out to a straight line that was 20, 30 feet further out. And so there was a certain danger to motorists here. What they've done on the new part of the Hood Canal Bridge, because only half of it sank, and they kept the old half, which is on the east side, and they built a new west side. And the east is on the left here, and the new part is on the right, the west side. What they've done there is, instead of having an opening where you simply float between two side pieces, they actually lift up the roadway on hydraulic jacks, and the part which is moving to make the opening, that slides underneath the part which has been lifted up. So it's kind of an over and under system rather than a side-by-side system. So I think you now know everything about floating bridges, so we should move on and look at another different type of bridge, which I will go straight ahead with here, and that's pre-stressed concrete bridges. And these are very, very common in the state of Washington. They're actually common over the whole country now, and they're really the workhorse bridge for medium-span bridges in the kind of 70 to 200 foot range. These pre-stressed girders seem to do a wonderful job because they're economical, they're very durable, you really don't need to do much to maintain them, and therefore they have very low life cycle costs. And this is the main reason why they become so widely used across the country. They were started in 1952, and we're still using many, many, many of them today, and they pretty much started in the state of Washington. For those of you wondering what pre-stressed concrete is, let's just try and put the course into 30 seconds here. If you have a regular reinforced concrete member, like a beam, and you load it with some gravity load, you drive a truck across it, then the beam will bend, and on the tension side, which is the bottom, the concrete will crack. Now, that is not remotely unsafe, because you have already put steel reinforcement in there to carry any tension forces, so from a safety point of view, it's just fine. But on the other hand, when the concrete cracks, it does two things that you don't really want. One of them is that if the concrete cracks, the member becomes a lot more flexible and the deflections become bigger, and that may become a problem. The second is that with cracks, water and de-icing salts and other nasty chemicals might get into the cracks and eventually corrode the steel, and that would be a safety problem. So what you can do is pre-stress it. And what you do is you put a cable through the concrete, and then you put a jack on it, and you pump up the jack, and you put a big stress in that cable. You then come along and put an anchor at the end where the jack was, and then you can throw the jack away. And what you're left with is some concrete which is pre-compressed by having this tension cable through it. If you imagine, it's a little bit like having a bunch of kids' blocks with a rubber band which is stretched tightly around them. They're squeezed together and the rubber band is in tension, and so far you've got no load on it. Now the good thing about this is that it delays the onset of cracking very significantly, and that massively changes the performance of the material. And again, it's one of these ideas like Andy Phone's Caesura. It's really clever because it's really simple. So here is one of the giants of the industry. His name is Art Anderson and lived in Tacoma. And he started with his brother Tom two things. One was a fabrication plant where they actually made these pre-stressed girders, and that plant is still there today. And that was the first pre-stressed concrete girder fabrication plant in the USA. The second thing he did was to start off a design company, which he called ABAM Engineers, and the A in ABAM are Anderson and Anderson, Tom and Art. Now, like all these people, Art was, I think the way to describe him is a highly intelligent, visionary knucklehead, because he was the kind of person who, if you wanted him to do something, all he had to do was say, Art, you know, I don't think this could be done. And he'd kind of grit his teeth and he'd go off and he'd do it. Whether you thought it was possible or not, he would make it happen. He was that kind of a guy. This is a picture of some pre-stressed concrete girders in place from about a week ago. They're up at Northgate in Seattle for Sound Transit. What you see is girders which look pretty skinny. They look like eye girders, almost like steel girders. And this is the way that this pre-stressed concrete industry is developed today. You might have thought of concrete as a rather lumpy, large, brutish material, but they're now very skinny, very high strength material, very highly stressed, and very efficient indeed. So here we see them being made in the factory in Tacoma, in Art Anderson's factory. And the way they do it is that on the left-hand side of the picture, you can see some orange frames where the jacks are. And these are pulling on the cables to stress them before they cast the concrete. And you see there's two sets of cables, which are actually known as strands in the industry. And some of them are in the bottom flange of the girder, and some of them are sloping downwards in the web of the girder, which is the tall, skinny bit. In the top flange, they typically don't put any. That's not quite true, but they typically don't put them. What they then do is they put the form together around these cables, cast the concrete. When the concrete has set up and hardened, they let go with the jacks. The cables try to shorten, but because they are now bonded to the concrete, which surrounds them, they can only shorten a very small amount, and the whole thing comes to equilibrium with the concrete in a lot of compression and the cables still with a lot of tension in them. So they then take them out of the forms and go and store them in the yard until they're ready for use on site. And you can see a couple of things here. One is the shape of the girders, these very tall, skinny eye shapes, very slender. But the other is they look like they're bent. And you think, did these guys make a mistake? No, they didn't. What happens is when they build them, they are absolutely flat and level and straight. When you let go of the strands after the concrete is hardened, and the force in the strand is then delivered to compress the concrete, they're compressing the bottom flange a lot and not compressing the top flange at all. So if you shorten the bottom and you don't shorten the top, then it will go into a curve, and it curves upwards in what we call camber. And you can see it quite clearly here. And if you ever thought that concrete was a rigid material, you're sort of right, but you can really see here that it's actually not. It does bend significantly. Well, after you've stored them, you have to ship them to site. And these things are getting big. There's no way that you can get them on a normal flatbed truck. They're way too big and too long. And the one that you see here is something like 150 feet long. So the way that you transport them is you put them on a special rig, and you have two trailers. One the front trailer and one's called the rear trailer, for obvious reasons. And each of those trailers had a lot of wheels anyway, just because the weight is so big that you have to spread the weight over an awful lot of tires so that you don't overload any of the roadways or bridges that you're crossing. And then the girder simply spans between the front and the rear trailer, carrying its own weight, because it's perfectly capable of doing that. You put a tractor on the front and off you go. But there's one more thing here. In the back, you may or may not have noticed, at the front of the rear trailer, there's a little cab, and you can just see it's got a kind of a white part on the cab there. This is necessary because you need to steer that rear trailer. So someone sits in that cab. They don't have any power available. That all comes from the tractor in the front. But they sit in the trailer, and they have to steer that trailer. And they are barreling along the highway at 60 miles an hour, and they've got a concrete girder weighing something like 100 tons about 2 feet above the head. And frankly, rather than me, and I hope they get paid a lot of money for doing that, because it seems like a very dangerous and skillful job. Then when you get to the site, then you take them off the truck, off this trailer system, quite carefully, and then you simply erect them on the bridge. And in that sense, they're a bit like a steel girder, in that you can simply put it straight up there. You don't need any wet concrete there. You just put the girder straight up. You do see some things look like they're bits of orange rusty metal on the side. And these are brackets which will hold the formwork, because on top of these girders, they will eventually cast a field cast concrete slab, because this is again the Sound Transit up at Northgate. They need a flat slab to put the rails on. So that's what will happen. That's what those brackets are for. So I think that's probably quite enough about prestressed concrete. And we should move on and talk about another type of bridge, which Maureen will introduce you to, which is the Pasco-Kennewick Bridge.
Pasco-Kennewick, yes, thank you, is two of the three cities that make up the area we call Tri-Cities, the third being Richland. Pasco and Kennewick are across the Columbia River from each other. Now, they are still largely farming communities, but Pasco got a Northern Pacific rail yard in the late 1880s, and that bridge you see back there is the Northern Pacific Railway Bridge. But until 1922, the only way to get people or automobiles across was by a 6-car capacity ferry. Getting a lot of people across was very difficult. In fact, the Pasco-Kennewick football teams, when they'd have their big rivalry game, the visiting team would charter a train to get everybody across. In 1922, they built the first Pasco-Kennewick Bridge, called the Green Bridge. It is a 2-lane steel truss cantilever bridge. And this was a cooperative effort between the two counties that the two cities are located in. And it was funded by communities all over the state because it was a really important major crossing in the early highway system of the state. It closed the gap in State Route 397, which was also known as the Inland Empire Highway. You can see here it crosses where the ferry route was, and in fact there is a grounded ferry over there on the side, on the right. And it served both communities very well. Well until about 1940, when the construction for a McNary Dam and the Hanford Nuclear Facility really started creating a population boom and a traffic boom, and the old 2-lane bridge became very congested and dangerous. They'd even treat it as a one-way bridge at times because it was so narrow. They'd let a car pass and then another car pass, and so it could be quite a mess. So in 1954, it was time to bust out the novelty scissors again for the opening of the second Pasco-Kennewick Bridge. It was built about a mile upriver, and it connected U.S. Highway 395. It did, however, divert traffic away from the city centers of Pasco and Kennewick. The Pioneer Memorial Bridge, which is nicknamed the Blue Bridge for the color of its steel through truss there, is a 4-lane arch truss bridge. It was the first steel tied arch design in the state. And it definitely improved conditions for driving, but it did decrease traffic into the cities of Pasco and Kennewick. So a gentleman named Ed Hendler, who would later become mayor, he was actively trying to get the old bridge, the green bridge, fixed up, or even have another bridge built next to it, to try to bring people back into their community. However, there was just no funding to be found for it. And then in 1967, the Silver Bridge collapsed over the Ohio River, killing 47 people. And the federal government started the National Bridge Replacement Program. So the federal government would pay for 75% for a new bridge. And Hendler, as I mentioned, wanted to do a second 2-lane bridge next to the 1922 bridge. But the Army Corps of Engineers said that its 13 piers in the water were too much of a hindrance for navigation. They wanted a 4-lane bridge with only 2 piers in the center lane of navigational traffic. So then came this gentleman, Arvid Grant. He was a Latvian-born engineer who came to the United States and settled in Olympia in 1951. And he had experience in Europe and post-war Europe with cable-stayed bridge construction. They were used to replace bombed-out bridges. And he really wanted to bring this technology to the United States. And this was the opportunity of a lifetime to cross a mighty river like the Columbia, as he put it, as a once-in-a-lifetime dream for an engineer. So his proposal, it fit the requirements of the Corps of Engineers, and its cost was comparable to other more traditional United States solutions to long-span bridges. So there it is. It was named for Ed Hendler, the man who worked tirelessly to get it funded. And there is the old bridge right next to it. There was a decade-long fight to save the Green Bridge for bicycles and pedestrian use, but the concerns for the navigation of the Army Corps of Engineers took precedent, and it was demolished in 1990. It's unclear if the new bridge really helped with the economic benefit to those cities, because of Hanford, the area has sort of a cycle of boom and bust, depending on what the government is willing to fund. But their economic constant is, and always has been, agriculture. But the bridge nonetheless made the crossing much safer and gave them a very beautiful landmark. Here it is at night. It was the first cable-stayed bridge in the United States. It was the second longest in the world when it was built in 1978. And it ushered in a new era of construction of cable-stayed bridges all over the United States. There's a new one that pops up just about on a yearly basis, and it was so appreciated that in 1985, President Reagan awarded it the first ever presidential award for design excellence. and it is the most recognizable Tri-Cities landmark. And to explain how they work, I'll hand it over to John.
Well, thank you, Maureen. It's a very handsome bridge. If we take a very quick jog back into history, cable-stayed bridges, the idea of a cable-stayed bridge is not new. A gentleman called Fausto Veranzio built one in Venice, but clearly not out of high-strength steel cables, way back in the 16th century. A few were built at different times in different variations during the 18th, 19th, and early 20th century, but they really got a boost, as Maureen was pointing out, after World War II. And there were three conditions that came together at that time. One was that pretty much all the bridges over the River Rhine had been bombed out by the Allies during World War II, so they desperately needed bridges rebuilt. The second was that there wasn't much steel around because it had all been used in the war effort. And the third was that there was a lot of ex-Luftwaffe engineers who no longer had jobs because the Luftwaffe had been disbanded by the Allies. So what you had was people with slick engineering skills and a real need for bridges, but very little material. So what do? You make a bridge which uses very little material and solves the problem. And that's exactly what happened. The two big movers and shakers here were a gentleman called Franz Dissinger and Fritz Leonhardt, the Franz and Fritz of the German bridge builders of the time. And they were the ones who really developed the system in Germany shortly after the war. And as Maureen pointed out, it was Arvid Grant who brought it to this country for the first one in 1978. Well, how do you build one? Well, we're back to the same thing we had been before, that when you design a bridge, you really, really, really have to think about how it's going to be built, because that determines whether it will be possible and largely the shape of the bridge. So you start with the Columbia River, and you come and put a column down in it, or two as the case may be. You then put a cable down, and then you build a short piece of deck. You can either build it prefabricated and float it in on the barge, which is a common way of doing it, or you can do something else. Then you do the same on the other side, and you balance the weight on the column. Then you do the same on the first side, and then do the same on the second side, and then you get bored of doing it individually, and you put them all up. So basically, you're putting a cable and a section of deck in, one after the other. And you may be familiar with, for example, the Port Mann Bridge, just behind Vancouver, BC. That was built in exactly this way. That's one of the bigger ones. What do the forces look like? Well, it's a fairly simple arrangement. You have tension in the cables, not surprisingly. You have vertical compression in the tower. Again, not surprisingly, that's the way all the weight is eventually coming down. What you get, which you don't particularly want, is a lot of compression in the deck. And this is kind of the price that you pay for having the tension in the cables. The deck is typically made as light as you can make it, because you don't want to have cables heavier than you have to. And typically what is done today is to have a deck which is supported on steel, either beams, or in this case here, a kind of trusses which go transversely across it, and then a concrete deck which is cast on top of that. And this is all done in an effort to make the pieces modular, so you can bring them in on a barge. You bring in whatever it may be, 20, 25 feet length of deck in a big piece, lift it all up on a crane from the barge, and then anchor it to a cable and go off and get the next piece. The bad news that we mentioned was that you have compression in the deck. And this actually gets bigger the closer you get to the tower, because all of the horizontal components of these cable forces are all adding up. And by the time you get back to the tower, there's some quite big horizontal forces in the deck. We are trying to make the deck light and as skimpy as possible so it doesn't weigh too much. So you have to be careful about buckling questions and material failure questions, and that's just one of the things that you have to deal with when you design a cable-stayed bridge. So I think that's probably all we need to say about cable-stayed bridges, except here we are looking at Arvid Grant's bridge again. Very handsome, very famous. And perhaps we should go on now to another bridge which is not famous but infamous, and let Maureen talk about that one.
Okay. Thank you. Yes, the infamous West Seattle Bridge. There it is, and the Spokane Street Swing Bridge below it. But Spokane Street, you can see in this picture from around 1900, that was a location of several low bridges into West Seattle, because West Seattle, which is located on a peninsula, and it's separated from the main part of Seattle by the mouth of the Duwamish River and the Tide Flats Valley Bay, which this area was, which is now all filled in and is what we call SoDo now. So the waterfront, the industry was on the waterfront. All of the residential and business community was up on the top of the bluff, and West Seattle was its own separate city until it was annexed by Seattle in 1907. So access was by steamer and ferry service until 1902, when the first low swing bridge was built at Spokane Street. And a couple years after annexation, the city built a new Spokane Street swing bridge. And part of the main reason that West Seattle voted to be annexed by Seattle was infrastructure concern. They wanted the electricity and water. And so to save on cost, the city used, you can see on either side of the bridge, those pipes. And that is how they carried the water supply to West Seattle. So every time a boat came along and the bridge had to open, they would turn off the water supply and uncouple the pipes. And so people in West Seattle couldn't turn on their water. It was a considerable nuisance that got worse as traffic increased and boat traffic increased. So by 1916, the community was calling for a high fixed bridge that would deliver residents, commuters, up to the bluff where their homes were. But instead, in 1918, the city built a second, slightly higher bridge to be there on a temporary basis. It's just until they figured out what replacement they were going to put there. This and the 1911 bridge handled the traffic pretty well. And in 1921, ferry service stopped. Growth was continuing. Traffic got very, very bad. So the calls for a high bridge were really reaching a fever pitch. However, the city again turned to bascules. And in 1924, they built the first of the two Spokane Street bascule bridges. And the second was built in 1930, and once they were both in place, they each carried directional lanes. And they served pretty well, but by the 1970s, traffic had gotten very bad again, and renewed calls for the high bridge once again came about. And funds had been approved in 72, but it was the 70s. Boeing bust, all kinds of things contributed to it not being built. And in 1978, when the mayor suggested refurbishing the old bascules, West Seattle was threatening to secede. It was very serious. It was getting ugly. And then an inebriated 80-year-old freighter pilot rammed into the north span in a freighter that had 20,000 tons of gypsum, and so it damaged it beyond repair. It was stuck in the open position. And because it was not fixable, it qualified for federal funding. So West Seattle was finally going to get its high bridge after over 60 years of asking for it. So in 1980, construction began on a cantilevered segmental bridge, and you can see there the 1924 bascule bridge was left in place, and it served the community while this bridge was under construction. And a replacement for that lower bridge was part of the funding package, and that was completed in 1991. So here they are together. The high bridge that handles the commuter traffic, and the low bridge handles the industrial and port traffic. And the low bridge is actually a pretty innovative bridge as well. It is the only concrete swing span in the world and the world's heaviest moving structure. And it was awarded with an outstanding achievement by the Society of Civil Engineers. But you have heard lately about the bridge giving us a bit of trouble, so I will hand it over to John to discuss that.
Thank you, Maureen. Don't like to be the one who has to deal with trouble, but there we are. Let's go back to the good end of it. When they were building the West Seattle Bridge, what they were faced with was the problem of building a bridge with a fairly long span, 590 feet for the main span, and about 375 each for the two side spans. They went with pre-stressed concrete construction. They actually had an option for doing steel or concrete, but the steel one came out to be quite a lot more expensive, and so economics dominated, and they built the concrete one. Then again, the question is, how do you build it over an open waterway when you cannot put false work down there? And we're back to our old friend, the cantilever construction. And here it's called balanced cantilever construction. So it's a very slight variant on what you might otherwise have seen. It's a terrible name because at no stage is the construction balanced. It is always unbalanced, but we'll have to forgive the engineers for getting the wording wrong. What you do is you build two columns, and they're big columns. They're 12 feet by 17, I think it is, square. And then you come along and you build a small portion of the deck structure, which is a big box, and you push it out so it's a little bit eccentric. So in this case, both pointing towards the middle. Then you build another one on the outside, which again makes you about half a segment eccentric towards the outside. So now the columns are bending outwards. So now you put another, you put another one on the inside, and now the columns are bending inwards. So you keep on putting pieces on the outside and the inside, the outside and the inside, always keeping the column very slightly unbalanced because you really can't do anything else. And then finally you do what they call a closure pour in the middle, where you connect the two up. Now, when you're building these things, you might ask, well, it's okay to just show the pieces flying up in the air. How do you stick them on? Well, the answer is you go back and you do the same operation of pre-stressing that we saw before. You put when you put the piece on and you're holding it up there with a crane, then you put a cable through, you anchor it one end, and you put a jack on the other end, and you pump up the jack tight, and you stress that cable. You come in and put an anchor on at the jack end, and then you drop the jack in the water and throw it away. And what you're left with is all these pieces which are squeezed together by these cables under high stress. And again, think of the rubber band. You've got a super big rubber band on steroids, which is squeezing all of these pieces together, and so that's how they manage to stay up. You do this on both sides, and in addition, when you've done the closure pour, you then put some additional cables in the bottom in order to take the weight when you drive the trucks over this thing. So that's how you build a cantilever cable stayed bridge. You can actually do it two different ways. One is that you can cast the pieces in place by putting a new form at the end, carried on a crane or force work. You can either cast them in place, or you can ship them in on barges as prefabricated, precast pieces, and then you can lift them up with a crane. And typically today, if you've got a big enough bridge and it's worth making a special casting yard, then the precast is probably the way to go because it's a little easier. But the West Seattle Bridge was built by using a cast-in-place technology. Just a couple of drawings, just to show you what the drawings for these things look like. And these are the drawings from the original bridge. And these are all hand-drawn. And so you can see the fairly elegant handwriting on there. These guys really took care with their handwriting. This is the bridge in elevation. You see the big main span and the two side spans. And the kind of box thing in the middle is just a drawing showing this is the navigation clearance that was required by the Coast Guard. If we look up close at some cross sections, if you look back here, you can see that the box is a lot deeper over the supports than it is at mid-span, and that is reflected here when we look at the cross sections. The deep one on the left is what it looks like back near the piers, and the shallow one on the right is what it looks like out at mid-span. And back at the piers, it's got a very, very thick bottom slab on it, much more so than when you're out at the piers. And that's true because you've got much bigger bending moments when you're back at the piers. Well, what about that post-tensioning or the pre-stressing? Well, here it is. You can see what looks like a pepper pot in the top flange with a whole bunch of holes in it. And these are the ducts which they pass the cables through. And you need an awful lot of ducts because it's made in an awful lot of pieces. And each piece needs its own cable and its own anchorage when you lift it up or when you cast it in order to anchor it back to the previous ones. Then you have to have a new anchor for the next one and every other piece that comes in. So all these little circles are cable holes, and the square things up at the top are in fact anchor plates where they anchor it after they put the jack on it. And down the bottom, the same kind of thing is true. So that's how you build it. What's happening now? Well, where the bottom cables end, there is an anchor point, and it's been circled in red there. And if you look at the bottom of the bridge, what you see is some cracks which are emanating kind of diagonally, and they happen to start exactly where the anchor for those bottom cables ends. And what has happened is that the forces from that anchorage are very large, and some of the other forces in the bridge have moved around a little bit thanks to creep in the concrete. And the result is that there are cracks which emanate from that bottom anchor point. And that is what is causing all of the problems today. So, in fact, but for a very small change in the original design, we would not be having any of the problems today. The rest of the bridge is, in fact, in remarkably good shape, considering it's 37 years old. So, I think the last question is, where do we go from here? What is the future of bridge engineering, and where are we going to go with it? Well, I think the first thing I would say is Washington State will continue to lead the way in innovation. And if you look back at history, you say we can boast the first ever floating bridges, and at the time they were the only floating bridges in the world. Thank you, Homer Hadley. We can boast the first pre-stressed concrete production plant in the whole country. Thank you, Art Anderson and Brother Tom. We can boast the longest steel cantilever truss bridge. This is the one over the Astoria Bridge over the Columbia River. It's the longest in the US, it's still true today. We can boast the first cable-stayed bridge. Thank you, Arvid Grant, for bringing it to this country, the first one in the US. We built a major suspension bridge, which is pretty rare these days, and that is the second Tacoma Narrows ones. And about a month ago, we just built the longest pre-stressed concrete girder that has ever been built in the world. Thank you, Concrete Technology Corporation. It's now over I-5 just outside Tacoma in a bridge there. So I think we've got a pretty good history of innovation, not just in this country, but in the state. Then you ask, well, what do we think is going to drive the future in terms of design and construction? What are the big forces which are acting on us? Well, I think anyone's crystal ball is probably as good as anyone else's, but the ones I would say are things like congestion in urban areas is getting worse and worse. And the result is that it's very difficult to build a bridge over a highway and put a column down wherever you want to, in the middle, to make two short spans, because that column will probably block off traffic somewhere on the highway below. So what you then wind up doing is just building longer girders. It also means that we have to use what we call accelerated bridge construction, which are techniques whereby you can try to reduce the amount of time that you spend on site, perhaps at the expense of a bit more preparation time up front, because that reduced site time will then help with the traffic congestion. Sensitive environmental areas we are much more sensitive to today, and again, these typically do the same kind of thing. You build bigger, longer bridges so you can jump over a sensitive area rather than having to put a column down there. The need for longer service life. Corrosion has always been a problem, and this will continue to be a problem. We're always looking for ways to slow it down. What tools do we have for innovation? Well, we've got new materials. We're always trying to make materials which are stronger, which are lighter, maybe more corrosion resistance. Things like carbon fiber were incredibly expensive only 20 years ago. The price has come down. It's being much more widely used now. Very, very strong stuff. New methods of construction, things called SPMTs, which we'll see in just a second, lateral slides, which we'll see in a second, and bridge launching, and we'll also see an example of that. And then I think we should add in computer technology, which is allowing designers huge extra openings in that they can deal with difficult geometries, which are never true before, difficult stress conditions, earthquake conditions, and it's made a huge difference to what we can do. A very quick look through then. This is an SPMT. And you can think of it as the world's biggest forklift, if you like, because it's called a self-propelled modular transporter. And you can see this thing has about 20 axles on this side, and there's another one on the other end, and it's carrying what looks like a huge concrete platform, which is in fact a whole bridge. And the way you build a bridge fast with these things is you find a field close to where you want to put the bridge, and you build the bridge in the field. And you're disturbing no people, just cows. You then go in with the SPMT, you pick it up from the field, and you go down the highway. You drive to the final location, and you set the bridge down. And then you go home. And the state of Utah has made extensive use of these things, and they've been able to replace a bridge over the freeway there in a weekend. They closed the freeway for a weekend, put the new bridge in, and then go away. And the first time they did this, they had something like 10,000 people came out to watch, just because it was such a spectacle to see this happening. Lateral slides are somewhat similar, but maybe less dramatic. And this is the Skagit River Bridge, which got hit by a truck in 2012, and they put the new bridge in 2013. And here what you do is you build what they call a skid bench, which is a temporary steel frame going transverse to the direction of traffic. There was a temporary bridge in place, which is an emergency Bailey bridge there. But they built the new bridge, the white thing, out to the side on the skid bench. Then what you do when the time comes is that you slide the existing bridge out on the skid bench, going to the left. Having slid it out, you then slide the new bridge in from the right. And this bridge was done in a special contracting procedure with WashDOT, who reckoned that the price that you offered for the bridge would be added to the time that it would take for I-5 to be closed. And they were charging something like $1 million a day to be added to your contract price for the bridge to be closed. And the person who won this was a company called Max Cooney Construction, and they sat down and worked out that the cost of closing I-5 was a huge part of the total cost. So they worked out a way to close I-5 for the very minimum possible time. And I think I'm right in saying that they closed I-5 for a total of 13 hours, just overnight. And they got the old bridge out and the new bridge in that time. The last one is called bridge launching, and this is a picture of the Millau Viaduct in France. It's not in the state of Washington, I wish it was. And this bridge itself is pretty extraordinary for other reasons as well. But it's built by bridge launching. And I like to think of this as the toothpaste tube approach to building a bridge. That what you do, you sit on one side of the valley, and you have a little shed where you make pieces of bridge. You then push them out over the valley, and in this case, the gray towers are permanent concrete towers, which would be piers for the bridge, and the red ones are temporary towers, and they each have essentially roller bearings on top of them. And as you push the bridge out, it comes onto the roller bearings, and it just rolls out, and the further you push it, then the further it goes, and you put a new piece of bridge in on the side where you're manufacturing bits of bridge on the side of the valley, and you just keep pushing it out. And what this does again is that it saves you putting up an enormous amount of false work to support the bridge as you're building it. To get a sense of scale, the central pier on this bridge, from ground level to the top of the pier, is 1,100 feet high. So you can imagine having to build false work that high would be a huge problem. Oops. So I just pushed the bridge out. So I think the last thing is the computer technology, what's that doing for us? And these are just some wonderful bridges that actually Angela managed to find. And thank you, Angela. There's some pretty strange geometries, and this you can do perfectly well if you've got computer technology, doing this kind of thing by hand will be a complete nightmare, and why we couldn't do it before. So I think with that, I will close our part of it. And I'd like to say thank you to my fellow speaker, Maureen, here. And I think, very much enjoyed doing this. And the next section is, if there are any questions, Craig, I think, is going to push them.
Yes. All right. Thanks, Maureen, and thanks, John. I think excellent presentations. And the first question is for you, John, and it's by far the most important one. It's from Lynn, and she'd like to know if those are Portland bridges on your tie.
There may be a Portland bridge here somewhere. There are actually a variety of bridges from different places. Yeah.
Okay.
Yeah, pretty Catholic in our tie taste.
Awesome. Yeah, so if you hadn't noticed now, you will notice now he had bridges on his tie. So
Yeah.
that was a good question. All right. So next question is Patty would like to know, in construction of floating bridges, are divers used in the construction of those floating bridges? I'm assuming for anchors or
Martin,
things
I need to
that.
answer that.
Marine?
Divers?
Yeah.
You know, I can't answer that with any confidence. Do you know, John?
I think the answer is no, unless something goes wrong.
Okay. Is that because of the depth, right?
It's
So
because of the depth. You're in 200 feet of water in Lake Washington, and that's not just a normal scuba diving drop. And it's dangerous. You don't want to be down there unless you have to.
Yeah.
So my understanding is no, they don't.
Okay, thank you. All right, we got another question from Karen. She asked, how often are gravity anchors and or blade anchors used in floating bridges?
Well, we got we got 4 floating bridges now in the state of Washington. I hope none have sunk while we're talking this, just in case. And there are a couple in Norway. They've got a couple in Japan. I think there's one in Canada. So there's probably maybe 10 in the world.
Okay.
And I think the preference would be for the gravity anchors if you can do it. The blade anchors typically you'd have to use only if you're in soft soil. And I think probably the ones in the fjords in Norway, the soil is really pretty rocky. Mm-hmm. And therefore you'll be using gravity anchors there if you do them.
Okay. All right. Another question. This is from Elizabeth. It said, prior to the introduction of the automobile, Seattle had an impressive system of earth and ash bicycle roads, also supported by earlier iterations of the Good Roads Clubs. Can you talk about the pedestrian or bicycle-only bridge innovations in Washington historically? I think this would be for you, Maureen.
Oh, well, yes, the Good Roads movement did actually start out by bicyclists, when bicycling became a big fad around the turn of the century. The Washington chapter formed later and was mostly concerned with building roads for automobiles. So insofar as building bridges for bicycles specifically, historically, I'm not exactly sure about that. There were bridges that were built for automobiles originally, like the Ravenna Bridge, which since I think the mid-70s has been closed to automobiles and is only for pedestrians use. But historically, in Seattle, back during this early automobile era, these bridges, the Basco bridges, they were all built with sidewalks. But as far as bridges specifically for bridges, no, not aware of any.
Okay, thanks, Maureen. John's asked, I think this one may be for you, John. It says, are cantilever bridges, example Deception Pass and Astoria, member-centric?
Are they what?
Member-centric.
I'm not quite sure what's meant by that.
Yeah, okay.
They are, in terms of how they're constructed, member by member, typically they would have been what in the trade is called stick-built. You bring along an individual piece and you put it in place rather than building a big module and putting that in place,
Okay.
which is what we would tend to do today, but the way they were building them then, it was typically stick-built.
Okay. Gibbons asks, what keeps the pre-stressed eye girders from being blown over on a windy day before the deck goes on top? So this would be during construction.
Occasionally nothing. there are historical reports that they do indeed get blown over. And in fact, when they get blown over, bad things happen because they are pre-stressed in such a way that the stresses that go in from the pre-stressing are just the opposite to the stresses which come in from gravity if everything is going right. And so they kind of cancel each other out in a very simple but clever way. If you knock them over sideways, then the pre-stressing is still acting, but it's acting horizontally. And there's no, well, on good days, there's no gravity acting horizontally. And therefore, in that case, they will camber and they will literally just bow out and just break their own backs. So if you push a pre-stressed girder over, it will probably be completely useless thereafter.
Okay.
So people take good care not to let that happen. And in today's world, with longer and longer girders, it's particularly important that before you let the crane off, you brace them properly at the ends and probably at midspan as well.
Okay.
And there's actually a case on I-5 last week, 2 weeks ago, when that nearly didn't happen.
Nearly didn't happen. Okay, good. Okay, so we got another question here, and it says, and maybe this can go to both of you. It says, do you have any thoughts about the best design for replacing the cracked Wesseal Bridge? If yes, why would the design be worth pursuing?
I'll let you
Say
do
that's
that one.
your purview. I don't know. I don't know enough about
I'm a bit too close
bridge
to that one. I
engineering.
think I'm not really allowed to speak about it. I'll let Maureen talk about it.
Fair enough. Okay, Angela, do we have any? Looks like we've got some more questions coming in. So, Hassan asks, in 20, 40, 100 years, what will be the most common bridge material?
Oh.
You want to crack at that one? What I think?
Well, there could be a material yet developed at that point, but I would wager pre-stressed concrete will still be a very widely used material,
Would
even 50, 100 years in the future.
yeah, maybe with carbon fibers? Or
I think it might be video cable. I think we might be all sitting at home and not having to travel anywhere anyway.
yeah.
No, I think clearly goods and services will still have to travel,
Yeah.
and therefore we should pay attention to that. Pre-stressed concrete is really on a roll, and it is looking like a very efficient, very durable material that will be there. I have no doubt that some of the more modern materials like carbon fiber will come into play. There is the potential. Can I answer that slightly at greater length? Can I get another 30 seconds on it?
You bet. Yeah.
Okay. If you use carbon fiber, has a strength. The good stuff has a strength of something like 20 times the strength of common steel on a per square inch basis. So it's unbelievably strong stuff. So what happens then is you really don't need very much of it, and so it becomes quite elastic, and you get quite big deflections. So if you to build a bridge out of carbon fiber alone, then it would be so bouncy, it would be like walking across a trampoline. And so these super high strength materials have that disadvantage that you come across not strength limits, but deflection limits rather quickly. And so even though we might say they're wonderful materials, you have to enter into a new way of thinking about designing with them and make sure that the configuration of the bridge you're building will be suitable for a material that has those characteristics.
Yeah. Wouldn't be comforting walking across a bridge with it moving up and down quite a bit.
Oh, I think anyone under the age of 10 would love it.
Yeah.
Be bouncing all over the place.
There you go.
Hey, look, Mummy.
Okay, so Elizabeth asked, what is the impact of soil type on the choice of bridge type? I think you kind of touched on that a little bit.
I think I would say you don't build it where there's bad soil if you can possibly help it, but of course then there is bad soil.
Yeah.
In fact, the original West Seattle Bridge, the one that's there now, they had to do a lot of soil improvement before they could put the foundations in. And it was actually great that they did that, because the foundations now are in really remarkably good shape. So I think the soil conditions might make you go to a floating bridge if you've got mud on the bottom of the lake, so that would be one
Right.
example. but typically what we would normally stuck with an alignment, namely the place where you can put the bridge, which is that you want it to be in line with an existing highway or something else, so you're kind of stuck with that. And you then are more likely to try to improve the soil conditions to suit the type of bridge which you have there. Maybe the other way to look at it, you would try to build a lighter bridge if you got worse soil, but typically you're going to build probably the lightest bridge that you reasonably can anyway.
Right.
With the possible exception, you might decide steel bridges are typically lighter than concrete ones, and therefore that might be a choice that would be driven by the soil conditions there.
Okay.
Can I give one other answer to that
you
one?
bet.
On the Skagit River Bridge, that was quite an interesting example that wasn't exactly soil, but nearly. When the truck hit the old bridge, they had a choice of using the existing piers in the river or building new piers. And it went out to design bid teams to say, which would you like to do? If you make a bridge which is 1 ounce heavier than the old one, if your new bridge is heavier, then you've got to put new piers in. And that will cost you, and the cost of your bridge will be much, much higher as a result. And you could think of that as saying the soil and the piers together will only hold a certain amount of weight. So the winning team, they bust themselves, they were going to make a concrete girders, and they bust themselves to use lightweight concrete, which just got in under the weight limit. And so they did not have to put new piers in. So that was kind of a weight limit question, which is similar to what type of soil are you having.
Okay, thank you. All right, so Richard's asked a question on the West Seattle Bridge. During construction, how did the contractor deal with the superstructure segment that contained low-strength concrete?
Are you up on the history of that one?
I wasn't.
Okay, I can tell you.
Okay.
What happened was that they detected by the color of the concrete that something looked funny. And then they started, because they always take cylinders to measure the strength, they discovered that the strength of that particular segment was coming up much more slowly with time than it should have been. And so immediately they decided to go back and they cut out that whole segment, jackhammered it out after, I forget how many days, but it was relatively young. And they jackhammered it out and they built a new one. Otherwise they would have had a terrible problem because they would have built out more and more segments beyond it and then suddenly found they had a bad apple way back there. Right. And they would have had to cut out all of these other segments as well. So it was a question of getting onto it very quickly, otherwise the cost of correcting it would have been huge.
Okay. All right, so Robert asked, steel railroad bridges, due to them having lead paint, are no longer painted and left to rust. What is going to be done in the future as corrosion weakens these structures to save them? I guess replace them, or
you got to pick them up and replace them eventually. There's a talk I gave a couple of years ago. We had some pictures of rusty railroad trusses in there, and one of the things that happens with them is, you want to kick in when I finish on this one?
Go ahead.
Is that the bearings on some of those old railroad trusses were typically steel roller bearings. And they're like a bunch of rollers sitting next to each other. And when they're nice and new and shiny and greasy, they roll beautifully. Mm-hmm. And the bridge can expand and contract under temperature just perfectly. And of course, nobody ever maintains them, and so they go rusty. And when they go rusty, they don't roll anymore, they lock up. And then when the bridge expands and contracts, it puts enormous forces on the concrete piers, and the concrete piers start to break up. And then everything goes to hell in a handbasket rather rapidly. And so it may not be the bridge rusting which finally kills it. It may actually be the damage to the piers due to these frozen up bearings, which is the bigger problem in the end. Or they both will be problems, but the frozen bearings are a major headache.
Okay.
Did you have anything to add to that, Maureen?
Nope.
Okay, so a question here from Michael. He says, I'm curious why there was no discussion about Galloping Gertie or other suspension bridges. Is there anything you could say, either one of you, briefly about those bridges?
Well,
first crack at it.
I think we didn't, we talked about including that, but it has been so widely discussed that we didn't. John did mention the second Narrows Bridge, but no, we had to cut some things out, select for time. But do you want to say anything engineeringly interesting?
Well, very quickly, I think Galloping Gertie was a stretch in terms of the proportions of the bridge and how shallow the deck was. And the proportions were much more extreme than any other bridge had been before that. Mm-hmm. And there were very few people in the world who really seemed to understand well the dynamics of bridges at the time. And there were a couple of theories running around which I think have been seriously discredited since then, and the bridge was designed according to some of those theories. And I think in the end it was way too flexible, and also the cross section was such that it picked up it shed vortices very readily, and therefore there's an interaction, an aeroelastic interaction between the wind and the structure, which kind of fed on itself and just got worse and worse and worse. And today, if we build a bridge of that type, we spend a lot of time and effort putting it in wind tunnels and making sure that it doesn't do that. In fact, there used to be, when I came to the University of Washington, there was an old wind tunnel in the lab, which is the one that Professor Farquharson had used to investigate that bridge after it collapsed. And it was a very small scale, but it was actually a pretty interesting device.
Okay. Looks like we got another question, and I think this is probably one that concerns a lot of people around the state. It says, Tasha asked, knowing that many of the bridges around the strait are reaching their expected service life, what are some of the more common vulnerabilities and suggested retrofits, or what retrofits are being done to address them? And I guess we have another similar question here. It says, kind of a couple interesting questions there. I guess the first one is, what do we do about the knowledge that we have about the older bridges around the state?
Do you want to take a shot at that one? Because I think there's only one Tasha that I know in the world.
Yeah. The second question, the bridge failures we've had around here have not been deferred maintenance. They've been engineering failure, or the pontoons be blowing in stormwater. But deferred maintenance is obviously a big concern. The viaduct had to come down because of its damage that couldn't be repaired, and it was already past the end of its life. We use them way beyond their intended life all the time. But John, you want to?
I think this is really a kind of political will and money question as much as anything else. Mm-hmm. For example, the West Seattle Bridge was built on an absolute shoestring. When they put it together, as Maureen was pointing out, they'd had a hell of a battle to get the money to do it anyway. And when they did, I learned the other day that someone said, well, why don't you leave the pre-stressing strands sticking out for an extra 6 feet or something beyond the anchors, so you could go back later and re-stress them or take them out and put new ones in or something. Yeah. And the answer was, we were trying to save every single foot of pre-stressing strand. Really? It was that tight. Now, how true that was or not, but this is a guy who worked on the bridge who said that. Yeah. So I think in some occasions we built the bridge under real financial pressure that you couldn't do quite as good a job as you'd like to. And then there's always pressure if you ask the city today, the maintenance money is always difficult to come up with, and the city has to allocate its money as best it can. So it is a permanent long-term problem.
Maureen, what would you suspect the average age of the bridge in Washington is these days?
Oh gosh, the average age.
Seems like most were built in the 50s, 60s.
We have a lot of bridges that were built in the 1910s or 20s. That was really the most sort of ambitious period of bridge building in Seattle. Math. I was told there'd be no math. Average age is probably maybe 50 years.
Yeah, that's probably about right, because I think there's a huge number of bridges which are built when the freeways were built, in that freeway building era, which is what the early 1960s. So that was another massive time. And those are now, whatever it is, do the math, 60 years old, they're coming up to their service life, end of their life. I think most of the pre-stressed concrete ones, for the most part, are in pretty good shape. Occasionally they get hit by a truck, and that's not fair, that's unexpected loading. But some of the steel ones, for example, they suffer from corrosion questions and fatigue questions, and those kind of gradually creep up on you, that they get worse and worse and worse, and you can patch them and do this and that, but eventually you just have to replace them. And some of the older reinforced concrete ones where the quality of the concrete was not that good, again, that allows the cracks and the spalling allow corrosion to attack the steel. And then once that happens, it's again a kind of a self-perpetuating event.
Okay. Are we doing okay on time, D'Angelo? Okay. So another question Scott is asking, have cable-stayed bridges replaced Golden Gate type suspension bridges for long spans?
It's an interesting question. There's kind of two schools of thought there. There's the supporters of the cable stay say, yeah, we're getting longer and longer and longer, and they are. If you go to a very long span, like the typical, the Akashi Kaiko bridge in Japan is the longest suspension bridge in the world, and its main span, I think, is inches short of 2,000 meters, which is what, 6,000 feet and a bit.
Yeah.
It's an extraordinarily long bridge. You could not do that at present with the cable stay, but the cable stay ones are getting longer. It really comes down to a question of cost. As they get longer, the tower has to get taller, and that really starts to cost you, because if you make it tall and skinny, it'll buckle, so you've got to make it thicker as it gets taller, and the tower starts to become very expensive indeed. But the cable stays are the Port Mann Bridge, which I think we mentioned. That is one of the longer ones out there at the moment, and that's a very successful bridge. They had a problem with ice on the cables, but they dealt with that.
Okay. So Bill asked an interesting question. He says, with the development of wood technology such as glulam beams and cross-laminated timber, which we hear about with the buildings these days, is it probable to see a resurgence in timber wood bridges? Probably for the length and span is going to be the limiting factor, I imagine.
Yeah, it's been proposed by, I think, some of the residents of West Seattle for the new West Seattle Bridge to have a giant timber arch bridge. I haven't sat down and done the math, but my feeling is if you try to make a timber bridge that long, the stress problem comes to get you, and timber is remarkably flexible as well. If you consider, if you just look at the flexibility of the material. A piece of oak doesn't feel very flexible, but you make it big enough and long enough, and it bends quite a lot. So I think for short bridges, and particularly pedestrian bridges and bicycle bridges, it's probably a fabulous material for within city. It would do very nicely. But for longer bridges which have got to carry truck loading, I think the answer is probably no.
Okay. All right, we have time for one last question. So Putman asks, how much emphasis do the organizations that build bridges put on the aesthetics or the appearance of the finished bridge? He notes that the Tri-Cities bridge is an attraction, the cable-stayed bridge in the Tri-Cities. So often is that
take that one, Maureen?
Well, I think that depends, like the political will and the desire of the community. That's an important. Generally, they see several proposals, and if that is a concern, then that would win the day, I assume. And I think that's probably was the case with the cable-stayed bridge in Pasco Kennewick. It was probably so impressive and beautiful when they saw the proposal, and the fact that it was economical was made it an easy sell.
I would second that and kind of add to it that sometimes bridges look elegant because they are what I regard as kind of spare and minimalist. There's no extra decoration, no extra stuff there. And the cable-stayed bridge at Pasco is exactly that. The only pieces of material there are working pretty hard. There are other cases, and I think I would quote in the San Francisco Bay Area, the new San Francisco Oakland Bay Bridge has a self-anchored suspension span as part of the bridge, which is a one-tower suspension bridge, which cost, I can't remember what it did cost in there, a staggering amount of money. And you could have put a bridge there far more economically, but the citizens of the Bay Area decided that they wanted a bridge that looked a bit like a suspension bridge, like many of the others down there, like the Golden Gate. And in order to get that appearance, they wanted a bridge which is built of that type. And so they went with something which pleases the eye of many of the area residents, apparently, but they got it at a staggering price. Staggeringly high, but not staggeringly low.
Okay, well, with that, again, I'd like to thank Maureen and John. Thank you for your presentation tonight. I think it was really informative, and it was fun to hear some of the history and then see on the technical side some of the limits and the things that we've done with bridges in the past and in the future. And with that, again, we thank you for joining us tonight, and I hope you enjoyed it, and hopefully we'll see you next year, maybe in person. Hopefully we will. But good night.